Hi, what's the speed of light? 299,792,458 meters per second. That's the universal speed limit, right? Everyone knows it. But here is something that might just bend your brain a little. What if I told you that we have never actually measured how fast light travels in one direction? We only assume it. And even more bizarre, we can't measure it, no matter how good our technology gets. So, what's one way versus two way? Here is how we do measure the speed of light. Shine a beam from point A to point B being a mirror, and then wait for it to bounce back. You time the whole round trip from A to B and back to A and divide by 2. That gives you the average speed. It's how most famous experiments worked, from lasers in the labs to early telescope observations of Jupiter's moon. But what if light goes faster in one direction than the other? Say it takes 4 seconds for light to go from east to west, and then 2 seconds from west to east. Average will be 3 seconds, even though the actual two-way speeds are different. So how can we ever know what's really going on out there? Before going to that, we need to know something called as the clock paradox. To measure one-way speed of light, you need a clock at the start and a clock at the end. Simple, right? You send a light pulse from clock A, say at 12, and then wait for it when it hits clock B. When it hits clock B, then you read the time. Boom, you get the time travel. Done. Except no, because now comes the question, how do you make sure that the two clocks are perfectly synchronized? Okay, you synchronize and set them side by side and then carry one to point B. Now relativity says that even a small movement can throw off its ticking. Okay, what if you sync them while they are apart? Let's send a light signal from A to B to sync the clocks. But wait, how do you know how long will light take to get from A to B? That's exactly what we are measuring. And that's the loop you can't escape. To measure one-way speed, you need synchronized clock. And to synchronize the clocks, you need to know the one-way speed. And believe me, back in 1905, Einstein was scratching his head to get around this puzzle. So in 1905, he said, okay, let's just agree as a convention that light takes the same amount of time to go from A to B as it does to go from B to A. Not because he proved it, but because it made the math cleaner and symmetrical. We call it Einstein synchronization. And guess what? It works. All our physics, from relativity to GPS, is built on this idea. But deep down, it's still just a choice, a very clever and a convenient choice. So that begs the question, what if light goes faster one way? Okay, let's just say, just for fun, let's assume that light goes faster going from east to west than, way back. Should we notice anything different? Actually, no, because every experiment we do is based on round trips. So as long as the average speed is same, physics still holds together. It's like hiding speed differences behind curtain. We never see what's going on back there. So even if light has preferred direction, we'd never be able to prove it. Not with clocks, not with lasers, not with any tool that we have today. So what then changes if the speed of light is different in one direction? You must have heard that when you look at the stars 1,000 light years away, you're seeing as it was 1,000 years ago. But what if we decided that light coming towards us is instant? Now that's interesting, because that would mean that you're seeing the stars as they are right now. Now, this is allowed mathematically. It's just different way of defining time. We're not changing physics or mathematics. We're just changing how we label moments in the universe. Now Einstein convention gives us one time. Instant arrival gives us another. Both work and neither can be proven right. So what's the truth? Does light travel same in all directions, or is there a cosmic bias hidden in plain sight? The answer is we don't know, and we might never know, because the moment you try to find out, the rules of measurements fold in on themselves. It's not a failure of science. It's a reminder that even our deepest truths depend on how we define time, space, and speed. The speed of light is constant only because we agreed to call it that way. And maybe that's what makes physics beautiful. So, next time when you look up at the stars, ask yourselves, are you seeing the past or just playing along with a cosmic convention? Thanks for watching.